Hello students, I hope you all are good. So our today's topic is magnetism and matter, NCERT section 5.4 and example 5.4 and 5.5. This is disclaimer. So learning objectives. After this lecture you will be able to understand the relationship between magnetization M, magnetic intensity H, and the roles in determining the magnetic properties of materials. Index, the topics that we are going today is example 5.4, then NCERT section 5.4, magnetization and magnetic intensity, and example 5.5. So first thing, example 5.4. So example 5.4 have 4 parts. So we will solve it part by part. So A part, magnetic field lines show the direction at every point along which a small magnetized needle aligns at the point. Do magnetic field lines also represents the line of force a moving charge particle at every point? Okay, so as we know that in electrostatics, the electric field lines, if positive charge is placed in electric field, so the direction of electric field also show the direction of the force acting on the positive charge. Similar thing, they are asking that if a magnetic field lines show the direction along which a small magnetized needle aligns. Okay, do magnetic field lines also represent the magnetic lines of force also? Do magnetic field lines also represent the direction of force on a moving charge particle? Okay, so this thing is conceptual, we have discussed in previous chapter also. Okay, so based on all the concepts we have studied in previous chapter and in this chapter, this is a conceptual question. So let's see the solution. No, magnetic field force is always perpendicular to B. We have studied that magnetic force is given by Q V cross B. So it is always perpendicular to B. It means magnetic field lines are not representing the direction of force. Okay, so this can be analyzed using the magnetic force formula, that is F equal to Q V cross B. Direction of magnetic force can be found using right hand thumb rule for vector products. Okay, we can find, align your fingers in the direction of velocity and curl your fingers in the direction of magnetic field, and thumb will give the direction of magnetic force that is perpendicular to both velocity and magnetic field. That means magnetic field lines are not representing the lines of force. Hence, magnetic field lines do not represent the lines of force on a moving charge particle at any point, because force is always perpendicular to the magnetic field. Understood? So B part, if magnetic monopoles existed, okay, we know that magnetic monopoles do not exist, but if they existed, how would the Gauss law of magnetism be modified? Okay, so what will be the modification in the Gauss law? According to Gauss law of magnetism, the magnetic flux through any enclosed surface is zero always. Okay, because magnetic monopoles do not exist, so inward flux will always be equal to the outward flux. So that's why magnetic flux through any enclosed surface will be zero always. But if monopoles existed, so what is the modification in Gauss law of magnetism? So let's see the solution. Gauss law of magnetism states that the magnetic flux through any closed surface is always zero. That is the Gauss law in magnetism. That is, closed integral of B vector dot ds vector is always zero. But what is given in the question now from Gauss law in electrostatics? Because we know that mono charges exist, isolated charges exist. Okay, so Gauss law in electrostatic is not zero. So integral E vector dot ds vector is equal to Q enclosed, that is charge enclosed by the closed surface, upon epsilon naught. Okay, if monopoles, magnetic monopoles existed, then the Gauss law for magnetism will be analogous to the Gauss law in electrostatics. Okay, so if monopoles existed, then using the analogy with the electrostatic, so replace E with B, replace 1 by epsilon naught with mu naught, and this QE, that is electrostatic charge, with QM, that is pole strength. Okay, replace these things. By drawing analogy, you can determine the Gauss law of magnetism if monopoles existed. That will be closed integral over enclosed surface B vector dot ds vector will be equal to mu naught QM. So this is the Gauss law of magnetism if monopoles existed. We can draw the expression by drawing the analogy to the electrostatics. Okay, if monopoles existed. If otherwise, we know that magnetic flux through any closed surface is always zero. Got it? Where QM is the monopole, magnetic charge enclosed by S. Okay. Now C part. Does a bar magnet exert a torque on itself due to its own field? Okay. We know that bar magnet placed in external magnetic field experiences a torque and force also on its poles, but net force on the bar magnet is zero in the uniform magnetic field. Okay, but is it possible that bar magnet exert a torque on itself due to magnetic field created by the bar magnet only, not external field? Okay, is it possible? And second part of this question is, does one element of a current carrying wire exert a force on another element of the same wire? Okay, so this is the second condition if there is a current carrying conductor or wire. Okay, so we will take two elements on this wire, two small elements on this wire. So the question is, does one element of the current carrying wire exert a force on the another element of the same wire? Is it possible? So these are the two parts of the question. Okay, so let's see the solution. No, there is no force or torque on an element due to the field produced by element itself. Okay, it is not possible that there will be a force or torque on an element due to field produced by that element only. Okay, so bar magnet will not exert a torque on itself due to its own field. It will only experience torque due to the external field. Okay, because magnetic field is in the form of loops. Okay, it is outside the magnet, it is originating from north and ending at south, and in the magnet it is originating from south and ending on north. Okay, so how this magnetic field can produce the force on the poles? Okay, so force or torque is experienced by a bar magnet only when it is placed in the external magnetic field. Second part, but there can be a force or torque due to one element of another element on another element of the same wire if these two does not lie along a straight line. Okay, if the conductor is not straight. What is the second part of the question? Does one element of current carrying wire exert a force on another current element of same wire? Okay, so the answer starts from third bullet point. But there can be a force or torque due to one element on another element of the same wire. But what is the condition? If these two elements will not lie along a straight line, means conductor should not be straight, or if the conductor is not straight also, but what is the condition? That these two elements should not lie in the same line or straight line. Okay, because magnetic field produced by any element along that element is zero according to Biot-Savart law we have discussed. Okay, because that r vector dl cross r, that r vector becomes zero if we are taking a point along that dl vector. So the distance of the point from the dl vector becomes zero. Okay, because due to that dl vector, theta becomes zero. Okay, if we take dl vector and a point along this dl vector for a conductor, then the formula for magnetic field according to Biot-Savart law, dB is equal to mu naught by 4 pi I dl sine theta upon r square. Then theta will become zero. Angle between that r vector and dl vector will become zero. Due to this, force along the dl vector, or magnetic field at the dl vector will become 0. Okay, so force or torque due to one element on another element of the same wire, if these two does not lie along a straight line. That means for the special case of straight wire, the force is 0. Otherwise, if wire is not straight, these elements are not lying in this one straight line, then it is possible that one element will exert force on the another element. This is because magnetic field due to current element along the other current element having same direction is 0. Okay, if wire is straight, the force or torque is 0. But if wire is not straight, these two elements lie on different lines, not along same line, then force or torque can apply on another element. Okay. Now, D part. Magnetic field arises due to charges in motion. Can a system have magnetic moments even though its net charge is 0? Okay, we know that due to the moving charges, moving electron, current arises. Okay, due to the moving charges, current arises, and due to this current, due to these moving charges, magnetic field arises. Okay, so can a system have magnetic moments even though its net charge is 0? So let's see the solution. Yes, the average of the charge in the system may be 0. Yet the average of magnetic moments due to various current loop may not be 0. Okay, we can say that the material we are given or the substance we are having, the average charge of this substance may be 0. Okay, it is not charged or it is not carrying also any charge. But the average of magnetic moments, there can be magnetic moments present inside, intrinsic magnetic moments. We are going to study in our upcoming lectures classification of materials, magnetic materials, that is paramagnetic, ferromagnetic, diamagnetic. Then we will learn about intrinsic or inherent magnetic moments that are present within the material already. Okay, so charge in the net charge on the system or material may be 0, but the average of magnetic moments that are present within the material due to various current loops. What are the current loops? Due to movement of electrons within the material, due to revolution of electrons, there are various current loops in the material, due to which average of magnetic moment may not be 0. It may be 0, it may not be 0. Okay, so this will become more clear when we will study paramagnetic materials in next section, where atoms have net dipole moment although their net charge is 0. The net charge on the system is 0, but they may have non-zero net magnetic moment due to the inherent magnetic moments due to various current loops. And these current loops are due to revolution of electrons within the atom. Got it? So we are going to discuss it in detail in that section. Okay. Now, next topic is NCERT section 5.4, magnetization and magnetic intensity. Okay, so you have to study this topic before magnetic materials. This is very important topic. So our earth is source of many elements and compounds. In addition, we have been synthesizing new alloys, compounds, and even elements. Okay, so many elements are there, many compounds are there. Our earth is a source of, okay, we are doing mining, we are extracting the ores. Okay, we are extracting different elements. In addition, we are also synthesizing alloys. Okay, alloys are not natural. It can be natural, but we are synthesizing many alloys to enhance the property of material. Okay, compounds, we are synthesizing semiconductor compounds. Okay, various compounds and even elements. Elements are all also being synthesized. Many of these elements and compounds possess inherent magnetism. Okay, so like some of the materials like iron, nickel, cobalt, or many other materials also, they possess inherent magnetism. Okay, So classification of magnetic properties of these substances becomes important. So we have to classify these materials, that what type of magnetism they are inheriting. Okay, so this is a type of whether they are if we bring a bar magnet or any magnetic material closer to that materials, are they repelling that magnet or are they attracting that towards that magnet? Okay, so what is the behavior of these magnetic materials? So they are classified on the basis of their magnetic properties. Okay, so it is important to classify them, to learn, to study about their characteristics separately. Okay, so we have seen that circulating electron in an atom has a magnetic moment. Okay, so we have seen that current loop, there is a current loop, circular current loop, due to which there is a magnetic field at the center. What is its value? Mu naught by 4 pi, mu naught I by 2r. Okay, that was the magnetic field at the center of a circular loop, and that circular loop is carrying current, and current is due to the moving electrons. Okay, if there is a electron, single electron, and it is moving in a circular path, okay, that can be considered as a circular loop, or that is equivalent to circular loop, but the amount of current will be very, very small, but it can be considered as current loop. Okay, so we have seen a circulating electron in an atom. So electrons are circulating in the revolution around atoms, around nucleus in the atom. Okay, so they are in circular motion approximately. Okay, so they are circulating in an atom, and it can be considered as a circular loop. And we know that a single circular loop, a coil, is considered as magnetic moment. A planar coil is considered as magnetic moment, and magnetic moment of this coil is given as M is equal to IA, current flowing through that coil into area of that coil. In the case of electron, the current due to that electron, okay, and multiply by the area enclosed by that circulating electron. So that is the magnetic moment of the circulating electron. Current due to that charge on the electron, and multiply by area enclosed by the circular path of the electron. That is the magnetic moment of the electron, as we study in the chapter moving charges and magnetism. Okay, so we are going to discuss about this magnetic moment of electron in detail. Okay, so you have to remember that throughout the chapter. In bulk material, these moments, now we know that there are number of electrons in a material, there are number of atoms, and in atom also there are number of electrons. Okay, due to each electron there is a magnetic moment. So these are individual magnetic moments of all the atoms, all the electrons. Okay, so in bulk material, these moments add up vectorially. Okay, the orientation or the direction of circulation of electron is different in different atoms. Okay, so that is some quantum thing. Okay, we are not going to deep into quantum mechanics, but we are you have to visualize that many electrons are rotating within a material or within an atom. Okay, so the orientation of this revolution of electron is different for every electron. Okay, so these moments, magnetic moments, due to all the electrons, because magnetic moment is a vector quantity. So magnetic moment due to all the electrons add up vectorially and may give rise to non-zero net magnetic moment. Okay, it can be zero. Their net magnetic moment of all the electrons in a bulk can be zero or maybe non-zero. Okay, so this is basically the concept behind the thing we are going to study. Now first one is magnetization. What is magnetization? There are two basic main terms that are magnetization. Another is magnetic intensity. Okay, so you have to remember the difference between these two. Okay, so what is magnetization? We are going to use that word, okay, widely. So what is magnetization? Magnetization is defined as net magnetic moment of a material per unit volume. Okay, so there is a, as we have discussed in previous slide, that due to all electrons and revolution of all electrons, there is a net magnetic moment. The individual magnetic moment due to all electrons get add up vectorially and give rise to net magnetic moment. So this magnetization is defined as the magnetic moment of a material per unit volume. Got it? Understood? So net magnetic moment per unit volume of the substance. So magnetization indicates, what is its significance? What is its physical significance? It indicates extent to which a material is magnetized. Okay, we are placing any material in the external magnetic field. So the extent, that how much material is magnetized, to what extent it is magnetized. So it indicates that extent to which the material is magnetized. It is magnetized more, it is magnetized less, or to which extent, how much. Okay, so mathematically it is represented as m equal to net magnetic moment of whole substance per volume of the substance. Okay, so according to definition, net magnetic moment of a material per unit volume. So mark it as 5.7 equation. So this is a magnetization. So extent to which material is magnetized. Okay, so like polarization. Okay, so this is equivalent to that. We have discussed dielectric polarization in electrostatics. Okay, so how many dipole moments are aligned? If, let's take a simple example. There are 100 dipole moments in a material. Okay, so there are 100 dipole moments in a material. I am talking about electrostatic, dielectric polarization. If I am applying external electric field and out of 100, 70 dipole moments align in the direction of electric field. So that means 70%, that is the extent to which material is polarized. Dielectric is polarized. Similarly, in magnetization, if there is a material, there are inherent magnetic moment due to revolution of electron. 100 moments are there, let's suppose. Okay, any arbitrary number, 100, 200, 300. Okay, 100 moments are there. Okay, and upon applying magnetic field, external magnetic field, out of 100, 75 magnetic moments align in the direction of magnetic field. So that is the extent to which a material is magnetized, up to 75%. Okay, so that is net magnetic moment. How much net magnetic moment appears? So the net magnetic moments due to the vector sum of all the moments. Okay, so 75 moments align in the direction of magnetic field. So net magnetic moment is 75. Let's suppose without units, 75 upon volume of whole substance. So it will result in that magnetization. Got it? So where m is a vector, so m is magnetization is also vector, because net magnetic moment is vector, so magnetization is also a vector with dimensions L inverse A and measured in a units ampere per meter. Got it? Now consider a long solenoid of n turns per unit length and carrying a current I. Okay, let's suppose there is a solenoid of n turns per unit length and carrying current I. The magnetic field in the interior of a solenoid, we know the formula. So what is the magnetic field in the interior of a solenoid, of a long solenoid, or if solenoid is finite, then near the center in the interior of the solenoid? Formula is given by, magnetic field is given by mu naught Ni. This is a formula we have studied in the previous chapter. So B naught is equal to mu naught Ni. Mark it as 5.8 equation, where direction of B naught is along the axis of solenoid. That we know that in the interior of the solenoid, magnetic field is along the axis of the solenoid. If the interior, now this is the magnetic field when solenoid is when there is a air or vacuum in the interior of the solenoid. Okay, I have discussed in that chapter also that how magnetic field, there was one or two lines at the end of that derivation, that magnetic field can be enhanced. Magnetic field in the interior of solenoid can be enhanced by inserting any material, magnetic material in the core, in the interior or core of the solenoid. That line was there, and now this thing we are going to study. Okay, so if the interior of the solenoid is filled with the material, now we are inserting some material in the core of a solenoid, between the windings of the solenoid, interior of the solenoid. Okay, that all things are same, in between the windings, core and interior, that is terms used for same thing. Okay, if the interior of the solenoid is filled with a material with non-zero net magnetic moment, what is it mean that non-zero net magnetic moment? That means material is having inherent magnetization, inherent magnetism, that material is having. Okay, so if the interior of the solenoid is filled with the material with non-zero magnetic moment, the field inside the solenoid will not be B naught. Now we have insert some material. Okay, now magnetic field in the interior will change, it will enhance, it will not be B naught now. Okay, because the material we are placing in the core of a solenoid, due to the magnetic field B naught in the solenoid, that material will get magnetized. Okay, that material will get magnetized. Due to magnetization, it will behave as a magnet. Due to magnetization, it will behave as magnet. It will produce magnetic field also along with the solenoid. So magnetic field will get increase, enhanced. Okay, the net magnetic field, now net magnetic field we will represent as B. B naught was the magnetic field when there is no material in the interior of solenoid. Now we have inserted the material in the solenoid. Now net B field in the interior of the solenoid may be expressed as B equal to B naught. B naught was there, and we have inserted a material, and this material is got magnetized due to the magnetic field of the solenoid. And after magnetization of the material, it will create magnetic field of its own. So magnetic field get added. This Bm is the magnetic field due to the material we have inserted in the core of the solenoid. Now net magnetic field will be B naught plus Bm. Okay, so it will get added directly. Even magnetic field is a vector quantity, but how is it is getting added directly? Because both the magnetic field due to solenoid and due to the material will be in same direction. Got it? So it will get added directly. So mark it as 5.9 equation, where Bm is the field contributed by the material core. As I've already mentioned, that Bm is the field contributed by the material core, because material core is magnetized. It is behaving as a magnet now. So it is contributing to the net magnetic field. This additional Bm is proportional to the magnetization. Okay, so it is proportional to. So what is magnetization M? This is the extent to which the material core is magnetized. So how much material core is magnetized? 75%, 60%, okay, 50%. So this is the extent. So this additional Bm that is being produced along with B naught. Okay, so what is this? This is proportional to the magnetization. That the larger the amount of magnetization of the material, larger will be the Bm. Bm is due to that material. Okay, so larger is the magnetization of material, larger will be the additional field Bm. So Bm is proportional to the magnetization M of the material and is expressed as Bm equal to mu naught M. Okay, mark it as 5.10 equation, where mu naught is the same constant that is known as permeability of vacuum that appears in Biot-Savitt's law. Okay, now magnetic intensity. So two things that we are going to discuss, more important things. One is magnetization, we have discussed. Now another term is being introduced, magnetic intensity H. Okay, so what is this? Magnetic intensity describes the strength of magnetic field produced by electric currents or magnets. Okay, so the magnetic intensity that is being produced by the solenoid when there is a no material core. Okay, due to the current flowing in the solenoid, the magnetic field B naught that was being produced, that is due to the strength of this magnetic field B naught will be represented or described by magnetic intensity. So magnetic intensity describes the strength of the magnetic field produced by the electric currents or the magnet. So it is the magnetic, or it is also known as intensity of magnetizing field. Magnetic intensity, or it is known as intensity of magnetizing field, the field that is used to do the magnetization. Okay, so initially we were having solenoid alone without any material core. So due to the current flowing in the solenoid, that field that is creating magnetic field was B naught, and that magnetic field, strength of this magnetic field is described by this magnetic intensity H. So this magnetic intensity is responsible for the magnetization of the material core. Okay, due to this magnetic intensity, magnetization is being done. Okay, it is responsible for the magnetization of the material core. Magnetic intensity describes the strength of a magnetic field produced by electric currents or magnets. Now, it is a measure of field's ability. Okay, so it is measure of what? Field's ability to magnetize a material. Okay, so it is the ability. Okay, if any person is able to do many things, so it is the person's ability to paint, person's ability to play cricket, person's ability to dance. Okay, so that is the ability. Okay, similarly, field's ability, what extent that field can magnetize a material, to what extent that field can magnetize a material. Okay, so if I am having H magnetic intensity, okay, so it can magnetize a material to 75%. I am having a particular material, so that magnetic intensity can magnetize it to 75%. So that is the field's ability. So it can magnetize the material up to 75%, means it can align 75 of the dipoles present in the material in the direction of it. Okay, so that is its ability to magnetize a material, and it is given by H is given by B naught by mu naught. It is similar to above formula, that Bm is equal to mu naught m. Now here B naught will be equal to mu naught H. Okay, from where H will be B naught by mu naught. Got it? That is similar to above formula. That is Bm is equal to mu naught m. Similarly, B naught will be equal to mu naught H. Got it? So H will be B naught by mu naught. It is now convenient to introduce the relation between H and M. So we can derive the relation between H and M now. So from equation 5.9 and 5.10, B is equal to mu naught H plus mu naught M. What was the formula? B was equal to B naught plus Bm. So what is B naught? Mu naught H. What is Bm? Mu naught M. So we can write it as, okay. Now, after rearranging this, find H from here. So H, take mu naught as common. Okay, it will result in H plus M. Okay, mu naught will go down in the denominator of B. So it will become B by mu naught. So H plus M will remain in the right side. So M will go in the side of B and get subtracted. So H will be, after rearranging this above equation, it will result in H equal to B by mu naught minus M. This is the 5.11 equation. This is the relation between H and M. Got it? Now, where H has the same dimensions, so H will be having same dimensions and units as M. So dimension of H will be also L inverse A, and units is ampere per meter. Both M and H having same dimensions and units. Now, does the total magnetic field B can be written as? So total magnetic field now can be written as B equal to mu naught. Take mu naught as common, as I have already mentioned, and it will be result in H plus M. This is the total magnetic field when material core is inserted in the interior of the solenoid. So mark it as 5.12. We have partitioned the contribution to the total magnetic field inside the sample into two parts. Okay, see, so we have partitioned initially magnetic field produced by the solenoid and B naught, and magnetic field produced by that material which is magnetized. Okay, B naught plus Bm. So we have partitioned the condition contribution to the total magnetic field inside the sample into two parts. So what are these two parts? One, due to external factor such as current in the solenoid. Okay, first contribution was due to the current in the solenoid, external factors. This is represented by H. And other is due to the specific nature of magnetic material. So second contribution Bm is due to the material core. So it is based on the specific nature of the magnetic material. Okay, so named as M. So we have partitioned the contribution. Now M can be, that M, magnetization, can be influenced by the external factor, and this influence is mathematically expressed as M equal to chi H. Okay, so M can be influenced by the external factors. What are the external factors? Like current in the solenoid, which is H. Okay, contribution due to the external factor is H. So M can be influenced by the external factor. Means if we are going to increase the H, M can be increased. So M is influenced by the external factor H. H is due to the external factor current. So indirectly M is also influenced by the external factor. Means if we are going to increase the current in the solenoid, that is external factor. If we are going to increase the current in the solenoid, H will increase because it is H depends on the external factor. So H will increase, and M can also be influenced by the external factor as this equation 5.13. M is equal to chi H. Okay, so this is a relation between M and H, another relation. Okay, where chi is dimensionless quantity. Okay, so you have also discussed or studied in electrostatic, chi E, that was electrostatic susceptibility. Okay, and now chi is here magnetic susceptibility. Okay, in dielectric polarization we have discussed chi E, electrostatic susceptibility. Now here chi is magnetic susceptibility. So what is magnetic susceptibility? It is a measure of how material responds to an external field. Got it? So how that material, that is we are inserting in the core of a solenoid, how it is responds to the external field. Got it? Second, chi is small and positive for materials which are termed as paramagnetic. That thing we are going to discuss in our tomorrow's lecture in detail also, but for a brief introduction, that chi is small and positive. Its value is small and positive for materials which are termed as paramagnetic. Value of chi is large and positive for material which are termed as ferromagnetic. And chi is small and negative for materials which are termed as diamagnetic. Okay, so it is a measure that how it is a measure of easiness, that how magnetic field lines are passing through any substance. Okay, we can also understand by this thing that magnetic susceptibility is a measure of easiness, how magnetic field lines are passing through the given material. Okay, so it is small and positive for paramagnetic, it is negative and small for diamagnetic, and large and positive for ferromagnetic. In the case of diamagnetic material, so for the diamagnetic material, chi is small and negative. That means the relation M equal to chi H. So chi will be negative. That means M and H are in opposite direction. M will be equal to minus something H. So because chi is of negative sign, so they both are in opposite direction. Okay, so how we will discuss in tomorrow's lecture in detail. Okay, from equation 5.12 and 5.13 we obtain. Okay, so we have discussed in previous slide that chi is small and negative for diamagnetic material. Okay, so that what is chi? Basically, chi is basically the measure of how magnetic material will behave in the magnetic field. Okay, or we can say it is the measure of how easy the magnetic field lines are passing through the magnetic field, material. So that is the susceptibility of material. How easy material is getting magnetized. That is a measure of that. Okay, so that chi value is different for different type of magnetic materials. Okay, we are going to discuss in detail in tomorrow's lecture also, but for a small brief introduction, so chi is positive and small for paramagnetic, positive and large for ferromagnetic, and negative and small for diamagnetic. So because chi is negative, so we know that the relation and m can be expressed as m equal to chi h. So if chi is negative, that means m and h are in opposite direction. Okay, so from equation 5.12 and 5.13 we obtain B is equal to mu naught 1 plus chi h. Got it? So what is this? We have expressed, what was the equation? That was B equal to mu naught total magnetic field, B equal to mu naught h plus m. Now we are replacing m with chi h. So h will come out as common. So in the bracket it will remain as 1 plus chi. Okay, so mark it as 5.14 equation. Now B is equal to mu naught mu r h, because 1 plus chi is can be represented as mu r. Mu r is the relative permeability. So mu naught into mu r will be mu. Absolute or permeability in vacuum into permeability in relative permeability will result in mu. Similar to that in electrostatic, epsilon naught into epsilon r will result in epsilon. Similarly, mu naught into mu r will result in mu. So mark it as 5.15 equation. Okay, where mu equal to mu naught mu r is magnetic permeability of the material, and mu r is equal to 1 plus chi, as we have seen in the equation also. So mu r is equal to 1 plus chi is dimension. Mu r is also dimensionless quantity and called relative magnetic permeability of the substance. Okay, now relative magnetic permeability is the analog of dielectric constant in the electrostatic. In electrostatic we have discussed relative permittivity, and that relative permittivity is equal to relative permeability was equal to dielectric constant. So it is analogous to that. Relative permeability is analog of the dielectric constant in the electrostatics. So magnetic permeability of the substance is mu, and it has the same dimensions and units. Mu have dimensions, mu not have dimensions, but mu are having no dimensions, because mu r is equal to mu by mu naught, the ratio of same quantities. So it is dimensionless and unitless quantity. Got it? So magnetic permeability of the substance is mu, and it has same dimensions and unit as mu naught. So mu is equal to mu naught mu r, and mu r is also represented by 1 plus chi. So this relation is also very important. You have to remember it. We are going to use that relation in tomorrow's lecture. Three quantities chi, mu r and mu are interrelated according to above equation, and only one of them is independent. If we are given one term, if we are given the value of one quantity, then we can find the other two quantities. Okay, so given one, other two may be easily determined. Now what is magnetizing current? Magnetizing current IM, this is the additional topic. Okay, you should know, because that thing is being used in your example. So what is magnetizing current? So magnetizing current IM, it is represented by IM, is the additional current that would be needed in the winding of the solenoid to produce the magnetization M in the interior of the solenoid if the solenoid was empty. Okay, Now we know that total magnetic field is B naught plus Bm. That Bm magnetic field is being produced by the material that is inserted in the core of the solenoid. Okay, if we remove that material, okay, so B will become B naught because Bm is now 0 because we have removed the material. But we want to produce the B, the initial B magnetic field. So what amount of additional current we have to give to the solenoid, that same amount of magnetic field B will be produced even if we have removed the material from the core of the solenoid. So that is the additional current that would be needed in the windings of the solenoid to produce the magnetization M that is being produced by material previously, but we have removed the material, so we have to produce the same magnetization or same magnetic field Bm. So what amount of additional current we have to give to the solenoid, that is the magnetizing current. From equation 5.10, magnitude of additional magnetic field is given by Bm, which is equal to mu naught M. Now if the core were empty, if we have removed the material, then magnetic field Bm, that Bm will be produced by the additional current Im. We are going to increase the current giving the additional current Im. So that Bm will be produced by additional current Im. So it is represented as mu naught Nim. So Bm will be now represented by mu naught Nim. So by comparing above two equation, M can be represented as Nim. Got it? So this thing we are going to use in the example. Now example 5.5. A solenoid has a core of material with relative permeability. Mu r is given 400. The windings of the solenoid are insulated from the core. Okay, solenoid is insulated, means the windings are insulated so that there should not be any short circuit from the core and carry a current of 2 ampere. If the number of solenoid is carrying 2 ampere current, if the number of turns is 1000 per meter, calculate H, magnetic intensity, B, magnetic field, total magnetic field, M, magnetization, and the magnetizing current Im. So here magnetizing current you should have to calculate. Okay, so that's why I have discussed the additional topic so that you can understand the example. Now let's do the solution. So given mu r is equal to 400 and I is equal to 2 ampere, number of turns per unit length is also given, 1000 turns per meter. Okay, firstly we are going to calculate A, H. Calculate H. Magnetic intensity H depends only on the current flowing through the windings of the solenoid. So H only depends on external factors, that is current flowing through the windings of the solenoid. In the absence of core in a long solenoid, magnetic field is given by B naught equal to mu naught Ni, that we all know. In the absence of core, when there is a no core, because H is only due to the current, not due to the material. Comparing it with B naught equal to mu naught H, we also know B naught is given by mu naught H. So comparing B naught equal to mu naught Ni with B naught equal to mu naught H, so it will result in similar to that equation, that Bm is equal to mu naught M and Bm is equal to mu naught Nim. So M will be equal to Nim. Similar to that, B naught will be mu naught Ni and B naught will be mu naught H. So by comparing, H will be resulting in Ni. So N is here 1000 and current flowing is 2 ampere. So H will be, magnetic intensity will be 2000 ampere per meter. Got it? So now B part we are going to discuss. B part, calculate B. The total magnetic field B in the interior of the solenoid will be given by B equal to mu H, that we have already calculated. So total magnetic field have several formulae. B is equal to B naught plus Bm. This is one of the formula. Okay, B equal to mu naught in bracket H plus H, B equal to mu naught in bracket H plus M. So it is one of the formulae. Okay, Another formula we have also discussed, B equal to mu naught mu r h, and eventually B equal to mu h from equation 5.15. Okay, we know the value of h. We have calculated 2000 ampere per meter. So how we are going to calculate the mu? Mu will be equal to mu naught mu r. Mu naught, we also know what is the value of mu naught, 4 pi into 10 raised to power minus 7. And what is the value of mu r given in the question? 400. So after putting all the values, B equal to mu r mu naught h. So mu r is 400, mu naught is 4 pi into 10 raised to power minus 7, and h is 2000. So after solving it, B will result in, we will getting the result, B is approximately equal to 1 Tesla. Okay. Now C part, we are going to calculate the magnetization, M. So from equation 5.12, we know that B, this is the one of the formulas of B, which is net magnetic field is mu naught H plus M. Okay, after rearranging, H will result in, M will result in B by mu naught minus H. After rearranging the above equation 5.12, we will get M equal to B by mu naught minus H. This is also the relation between M and H. So we know all the values. We know the value of B, which is approximately equal to 1 Tesla. We know the value of mu naught and H also. So after putting all the values, M will be 796000 minus 2000 will be, it will result in 7.94 into 10 raised to power 5. And we can take the approximate value also, 8 into 10 raised to power 5 ampere per meter. We are going to use the value of M in the further part D. But we are going to use this value, the accurate value, 7.94 into 10 raised to power 5. This is the approximate value. Okay. Now D part, the magnetizing current IM. Okay, calculate magnetizing current IM. So additional field produced due to the magnetization of the material is BM. Okay, which is due to the material inserted in the core. So additional field is produced by Bm equal to mu naught M. Okay, mark it as first equation. Now, if core were empty, if we remove the material, then magnetic Bm will be produced by the additional current we are giving, Im. So it will be Bm equal to mu naught N Im. Mark it as second equation. Now compare 1 and 2. So it will result in Im will be equal to M by N, which will be equal to 7.94 into 10 raised to power 5, which is the value of M we have calculated in the previous part, upon 1000, which will it will result in 794 ampere. So Im will be 794 ampere. So it is a large amount of current we have to give to the solenoid to produce the same magnetic field Bm that was produced by the material inserted in the core. Okay, so that material is enhancing the magnetic field to a great extent. So since this is a large current, showing that the strong effect of the core. Okay. So summary, what is magnetization? It is defined as the magnetic moment of substance per unit volume. M is equal to total magnetic moment per volume. Magnetizing field, measure of field's ability to magnetize a material, and it is given by H is equal to B naught, B by mu naught minus M. What is total magnetic field? It is given by B equal to mu naught H plus M. Magnetic susceptibility, chi, measure of how a magnetic material responds to an external field, and it is given by chi equal to M by H. Relative permeability mu r, it is given by mu r equal to 1 plus chi M. Chi M is the magnetic susceptibility. Magnetic permeability mu, it is given by mu naught mu r. These are all the formulas that we have studied in today's lecture. Okay, there are some practice questions. Define magnetization. How is it related to magnetic moment per unit volume? Explain the physical significance of magnetic susceptibility. How does it help in classifying magnetic materials? A long solenoid has 1000 turns per meter and carries a current of 1 ampere. So you have to calculate the magnetizing field H inside the solenoid, and another thing, the magnetic field B if the core is filled with the magnetic material of relative permeability 5000. Means mu r equal to 5000. Got it? So thank you, but please remain in the meeting for DPP section. Okay. First question is, which of the following correctly defines the magnetization M of a material? Net magnetic moment per unit mass, net magnetic moment per unit volume, total magnetic moment divided by number of atoms, or magnetic field per unit current. So you can write your answer in the comment section, A, B, C or D. The magnetic intensity H is related to the total magnetic field B and magnetization M by H is equal to B naught, B by mu naught plus M, H is equal to B by mu naught minus M, and H is equal to mu naught B minus M, and H is equal to mu naught B minus M. Okay, B. Next, for paramagnetic materials, the magnetic susceptibility chi is large and positive, small and positive, small and negative, or zero. Okay, second. If relative permeability mu r of a material is 400, then what its magnetic permeability? 400 mu naught by 400, 399 mu naught, or 401 mu naught. We know that mu is equal to mu naught mu r. So mu r is given 400. So what is mu? Okay. In a solenoid with a core of relative permeability mu r, the magnetic field B inside is related to H as B equal to, so total magnetic field is given by B equal to mu naught H, B equal to mu r H, B equal to mu naught mu r H, or B equal to mu r by mu naught H. So which option is correct? Yes, third option. So all answers are correct. Well done. So I hope you understood the today's lecture. Thank you.